You'll notice I've already got my equipment out in front of me. In addition to that, I do have my handouts with both the handout that I sent you for lab as well as the data sheet. Okay, and this data sheet's going to come in handy because we're going to have to do some translation from what is on the handout to what's in the data sheet. All right, so make sure you've got both of those available to you before you try to do lab today. This is going to be the most complicated lab you've ever had to assemble. And unfortunately, or fortunately as the case may be, as we get further in the semester, your circuits are going to get more complicated, and then you're going to wonder why you thought this one was so difficult. And so anyway, we're going to go ahead and get started. I've got my breadboard out. I'm going to turn it around vertically where the numbers and letters are upright, the way that I prefer to assemble my circuit. I've got my breadboard power supply. I'm going to go ahead and plug that in. And this week, because we're not going to be pulling that much current, I'm just going to use the 9-volt battery and adapter again. If you want to use the wall wart, you're perfectly welcome to use that, but at least for now I'm just going to use the battery pack. Now I'm going to go ahead and put in my 555 timer chip onto the breadboard, and this is a critical thing that you need to be careful about. When you first get the 555 timer chip out, these legs are not that rigid. They are very easily bent, and you want to be careful with that. And so you want to inspect your chip, make sure that the legs on the chip are not skewed one way or the other. All right, that's the first thing you want to watch out for. And usually with a brand new chip, the legs are not lined up exactly right to fit the breadboard, so do not force it. Okay? What you want to do is just gently set it into the breadboard and see if the legs line up exactly into the pinholes. If they don't line up exactly in the middle of the pinholes, do not push down on it. You will bend the legs on this thing. And so what I like to do, typically what happens is that whenever you get a new chip, the legs are splayed outward just a little bit. They're spread a little too wide. And so to bend those in, what you can do is take the chip, lay it on its side, like so, and then gently apply pressure against a hard surface, and that'll bend all 4 pins by the same amount, and just go a little bit. You probably only have to bend them less than 1 millimeter. You won't have to bend them far at all. Once you've done that, you want to orient your chip where pin number 1 is in the upper left-hand corner. So on my particular chip that I'm using today, I've got the indented circle that is right here on my chip. Yours may have that, or yours may have the half moon that's at the top of the chip. Either way, that'll let you know where pin 1 is. So I want pin 1 to be in the upper left-hand corner, and having done that, I'm then going to go ahead and place it, and because I know what's coming in this experiment, I'm going to tell you, go ahead and place it about 2/3 of the way up your breadboard. Okay? And so what you want to do is make sure that the legs line up exactly in the holes of the breadboard, straddle the channel. You remember that the pins on our breadboard do not connect across the channel. These holes are all connected to each other, but they're not connected over here. So this allows us to isolate our connections on this side from that side. And so once you're sure that your chip has been inserted properly, or at least it's lined up properly, press with an even amount of force across the entire chip to seat it into the breadboard. And it should press in where the bottom of the chip, the bottom of that casing, is flat against the breadboard. Okay, so it should be firm. Word of caution, whenever you get ready to remove your chip later after lab is over, I'll try to remember to mention this, but if I don't, you want to apply an even amount of pressure lifting up because you will bend those legs otherwise. They do make a special tool for doing that where you reach on either side and pull straight up. But if you're very careful, you grip with your thumb and forefinger and don't try to pull it towards you or away from you because you will bend those legs. Try to apply even pressure to lift straight up. Don't force it, and if you do that properly, you shouldn't bend the pins. But if you try to go that way or this, towards you or away from you, you will bend those legs. And you can straighten them back out, but it's just aggravating, and sometimes you have to use needle nose pliers to do it and such. Okay, so I've got my 555 chip seated properly. The experiment calls for setting up monostable mode first. Now I've given you the circuit diagram for that, and we'll talk about this in class on Thursday so that you'll be familiar with it, but you can already tell what you're going to need. You're going to need 3 resistors. R1 and C1 are going to form our RC charging circuit that's going to control our timing. Okay? R2 is here as a pull-up resistor, and I hope we'll be covering that in class tomorrow, but if not, I'll go ahead and explain the purpose of R2 now. And if you can't see it on my on the video screen here, you've got your handout with you. But R2 is intended to make sure that this pin that's labeled trigger, that's what it's connected to, is never floating, that it's never an open circuit to it. Okay? When the switch is open here, this trigger pin is still connected up here to our 5-volt power supply. Whenever I close the switch, I will then short that pin to ground, but the presence of the resistor to make sure that I don't short my power supply to ground. See, I've got a direct link between this power supply down to ground, but it's through that resistor. If that resistor were not there, then whenever I closed my switch, I would end up shorting out my power supply, and I don't want to do that. So I put this resistor in place, and the exact value really doesn't matter. It can be anywhere between 5K and 100K and be perfectly fine. I just happen to choose 10K, but it doesn't have to be. Okay? And so that's why I've done that. So basically what happens is that when the switch is open, then 5 volts is applied to the trigger pin, and whenever the switch is closed, 0 volts is applied to the trigger pin. So this is called a pull-up resistor because it pulls up the voltage whenever the switch is open. Okay? And then our third resistor over here is simply our current limiting resistor to our LED. As we said, these labels are on the circuit diagram, but in order to interpret that, we're going to have to use our data sheet. And so I'm going to set aside the breadboard for just a moment so that you realize that when we're doing electronics, quite often we have to do something extra. You know, this is not cookbook type stuff. You are expected as a professional to be able to translate things a little bit. And so let me go ahead and show you how we're going to do this. If you'll notice, each of the pins on the 555 timer from the data sheet are labeled. Ground, trigger, output, reset, control voltage, threshold, discharge, VCC. Those labels correspond to the same labels you see on this chip diagram in the lab handout, but the order is not the same. And so we're going to have to translate things a little bit. And to make things simpler, what I'm going to do is I'm going to draw the 555 timer chip out with its 8 connections, 4 on each side, like so. And I'm going to label those 1, 2, 3, 4, 5, 6, 7, 8. And then I'm going to translate this lab handout into how this chip has got to hook up. Okay, so I'm still going to keep my power supply over here the way it's illustrated, just so I can understand how things work. But you'll notice ground has to connect there, but ground is pin 1 from my data sheet. So that tells me that pin 1 has to go to ground. Okay. Pin 2 is this trigger pin, and we'll get back to that in a moment. What I want to do is go ahead and show my power connection. So pin 8 is positive power. So I'm going to wrap this on around. Notice I'm drawing the lines very large because when I start having things cross over, things may get a little complicated. Okay? Now, because I'm trying to draw this similar to how I'm going to put things on the breadboard, I'm going to have to deviate a little bit from the diagram that's in my handout here. Okay? Because I can tell already that my discharge and threshold pins here that are connected to my RC charging discharging circuit are actually pins 6 and 7. And so I'm going to actually end up drawing R1 and R2 over on this side. I'm going to draw them down further here to get them out the way. So that's going to be R1. Let me get up into the field of view here. And then my capacitor C1 is going to be there. And my capacitor has to connect back over to my ground connection. And the top of my resistor R1 has to connect to my positive 5 volts. So I'm going to connect it up like so. All right. Now, hopefully you're able to see what I'm doing here. Okay, so this is what I've got thus far. I've got my 5-volt power supply. I've got my 8 pins of my 555 timer. I've applied ground connection to pin 1, power to pin 8, and then I'm also applying 5 volts to my RC network. It's going to be charging and discharging. Okay. All right. Now, in order to make things a little simpler, okay, the next thing I'm going to do is to go ahead and deal with pin 7 and pin 6. You'll notice that pin 7 and pin 6 on our data sheet are labeled discharge and threshold. So I'm looking for those here, and you'll notice that pins that are labeled discharge and threshold are both connected between the resistor and the capacitor. So that's going to make life pretty simple. So I'm just going to bring this down here and connect it right there like so, and I can just connect pin 6 to that same place there. So pin 6 and pin 7 are both going to connect between R and C here, R1 and C1. Okay. All right, pin 5 over here is labeled on my data sheet as the control voltage. So I go back to my schematic here, and my control voltage just goes to a tiny capacitor. And what that is in your kit, I'll show these to you later, are your small, what we call ceramic capacitors. These are the ones that look like little bugs that have 2 short legs, but then they have a brown top to them, and I'm getting them all tangled up in here. So it's one of these type capacitors, okay? And so the exact value of it doesn't matter. I put down 10 nanofarads, but it really doesn't matter. And because we're designing our circuit not to depend too strongly on that. But that capacitor is connected between the control pin and ground. Well, the control pin is pin 5, so I'm just going to come down here, put that capacitor in, and on the schematic, that's what's labeled as C2. Okay. All right, let's work our way on around. Pin 4 on my 555 timer, if I look at my data sheet, is labeled reset. When I look at my schematic here, the reset pin is just tied to the 5 volts, and that's a digital input pin. And its sole purpose is to be sure that the chip does not automatically or does not accidentally reset in the middle of the experiment. And so I'm going to have to draw it like so. I'm going to jump across that connection and come up here to my 5-volt connection. Okay. That just leaves pins 2 and 3. Well, pin 3 on my data sheet is labeled as output. And for that, you'll notice on my schematic, output just goes to a 220 ohm resistor and an LED. So again, I'm going to have to draw a little jump across here, come down, resistor here, and this is R3. And then this circuit symbol diagram for an LED is that. And then I'm going to connect that to my ground connection here. Okay, pin 2 is the only one that's left, and this is the one that's going to be the most difficult one to get right. Okay, and so what we're going to do is the following. Pin 2 is that trigger pin you'll see. And that trigger pin on the schematic is connected to a resistor that's connected to 5 volts, and then we have a switch down below. So if we follow what the schematic says, we should be okay. I'm going to have to do a jump across here again. I'm going to bring down a 5-volt line to a resistor. This will be R2. I want to use the same numbering scheme on my hand-drawn circuit diagram that matches this. I'm going to jump across here, connect those two, come down, and now I'm going to have my switch connected to ground. Okay. Now with that, I want to double check my circuit diagram and make sure everything is okay. All right, so I've got my 5-volt power supply. I should be providing power to pin 8, 5 volts, and there should be no other connection to pin 8 except that I am pulling power to come over here. But this is not really so much connected to pin 8 as it is just connected to the 5-volt power supply. Okay, my RC charging circuit should be over here so that it's easily connected to pin 6 and 7. I know in the schematic it's on the left side of the chip, but the chip layout is such that it's easier to put it on the right side in physical reality. Okay, pin 6 and 7, the discharge and threshold pins should be connected between the resistor and capacitor, which they are. Pin 5 is my control voltage, and it should go strictly to a capacitor C2 over here and then down to ground, which it does. Okay, pin 4 should just go up to our 5 volts to our power supply, because that is our reset pin, and it does. Okay, and then pin 3 should go to our LED down to ground, and then like I said, pin 2 by far and away is going to be the most difficult thing to keep straight. You want to make sure that you've got R2 going up to 5 volts and then this switch down below. Okay, all right, now that we've drawn our circuit diagram, I'm going to go ahead and put in values here. This one is going to be our 220 ohm resistor. R1 is, for the beginning at least, when I read the actual illustration here, or I read the instructions, it says to go ahead and let R1 be 100,000 ohms, and that's just for this first part. So I'm going to write that there. And then our capacitor is going to be 100 microfarads. All right, staying organized as you're doing this is key. You cannot be lax about things and just wing it. You will make a mistake, you will mess up if you don't get organized as you're putting things together. Okay, C2 up here is that 10 nanofarad or just a tiny ceramic capacitor, doesn't matter what it is. R2 up here is a 10K ohm resistor, that's that pull-up resistor we were talking about earlier. And then this is our LED there. So we've labeled everything. So the actual number of components isn't that many, it's just there's a lot of connections to make. All right, so I'm going to go ahead and get my hand-drawn circuit diagram over here. I'm going to place my breadboard back in place, and I'm going to start assembling. Now, there's another device that needs to be put onto the breadboard, and that is one of our switches, and that will be found in the little external plastic case. You'll see that you've got several of these little push-button switches. They've got 4 legs on them, and so they look like a kind of a bug. And if you push down on the top, it's just a momentary push-button switch. So you push down to hold it, and it's engaged or turned on. When you let up off of it, it turns off. Now, just like with the 555 timer, what we're going to do is we're going to use that to span the gap here of our breadboard, just like before we seat it. We're going to see if the pins line up. In my case, it doesn't. The legs are actually in a little too tight to each other, and so what I'm going to have to do is to spread those legs apart a little bit, and I'm just going to use a flat surface here, and because I want to bend both of these pins the same amount. And I'm just going to spread these pins outward a little bit so that they fit into my breadboard a little better. Okay, not too much at once. It's trial and error, so test it out. And now I've got those pins lined up, and I'm going to go ahead and seat that switch into the breadboard. I won't push on the switch itself. I'm going to push on either side of the switch using my thumbnails, and that ensures that it is seated properly. Okay, now I can test my switch to make sure that it's working properly by using my multimeter and testing continuity. And one of the things that we do there is we can turn our multimeter to our resistance measuring location. I've got my 2 probes here, and when the 2 probes are connected and I have a continuous connection, I have 0 ohms. So if I place these probes alongside the legs of the switch on one side or the other, okay, so I don't mix and match. So on both sides here, you'll notice that I have an overload, that is, I have infinite resistance, and yet when I push the button, it should go down to 0 ohms, which is indicating that the switch has closed. I let off the switch and I go back to an infinite resistance again. Okay, so that's working properly. All right, well, let's go ahead and begin to place our components there. And I'm going to speed things up here a little bit in order to make life simpler for you. Our 100 microfarad capacitor, you'll also see is inside your kit. It will be labeled as such. It will be labeled 100 microfarads on the side here, and it's rated for 50 volts. You'll notice there's a stripe on this side that has a minus sign. This is what's called an electrolytic capacitor, and that means that it does matter which side you hook up to positive and which side to negative. Now, for space considerations for later, what I want you to do is to go ahead and put the capacitor down in this lowest row of your breadboard. So the negative lead of it should be down here, okay, and we'll worry about wiring it up later, okay. And so as you're looking at it from this angle here, you'll see the negative lead is in the last row, positive lead is just somewhere up here. Okay. Now I am going to go ahead and start making some connections with my jumper wires just so we can keep track of things. Okay. And you're welcome to use the color coding on the wires to help you keep things straight. I sometimes do, but not always. And so in observing my hand-drawn diagram here, I can tell pin 8 needs to go to 5 volts. Well, this whole red rail should be 5 volts if I have put my power supply in properly. If I look at my breadboard power supply, don't forget this pin up here that says plus should be lined up with that red line. If it's not, that means you've got your breadboard upside down. Okay? And then the negative should be on the blue rail. Same thing on this side. Now we're just going to use the left rail today. Alright? So pin 8 of my 555 timer should be connected to 5 volts. I'm going to put my jumper wire there, jumper wire there. Okay? Another word about jumper wires I do want to reiterate is that whenever you're removing jumper wires from your breadboard, don't grab the wire and pull this little black boot that's down here at the bottom. Just grab that and lift, okay, so that you can extend the life of your jumper wires. Okay, so pin 8 connected to 5 volts. Pin 1 is supposed to be connected to ground. So I'm going to go ahead and do those connections right now just so I don't forget to do them later. So I go there, and then I go into one of the ground holes there. All right. After that, it's just take things in turn. Okay. So for pin 2 has this 10K ohm resistor, and because I've drawn things the way that I have, I'm going to go ahead and make sure that I assemble it where it more or less on the breadboard looks similar to how I've drawn it. That'll help me check things out too. Okay? Now I've got a 10K ohm resistor, and as I said earlier, the exact value doesn't matter, but I do want to go ahead and confirm that it is a 10K ohm resistor. I'm going to put my resistor flat on the table, use my probes to press firmly on both sides, and it measures 9.95 kilo ohms, close enough to 10,000 ohms. So I'm going to actually place it above the 555 timer up here. I'm going to turn my breadboard sideways for perspective's sake so that you can see. And I'm going to make sure to put it into 2 blank rows up here. So I insert that into the resistor, this into the resistor. Okay. Now again, referring back to my circuit diagram, this is what is connected to pin 2. So pin 2, I've got this resistor. The upstream side of that resistor should be connected to 5 volts. So I'm going to go ahead and do that connection now. Okay, so let me turn this sideways again for perspective so you can see it. Upstream side going to 5 volts. Okay. Now the downstream side of that should connect to pin 2. So the downstream side of this same resistor should connect to pin 2. And so you have a variety of lengths of wires. Unfortunately, I always seem to grab the longest wires for things. And so I'm going to put this wire into the downstream side of that resistor. And then I'm going to connect it to pin 2. I'm going to have to kind of wiggle my way around the spaghetti wire. And I'm going into pin 2 right there. Okay. Now as I trace that, now I come down into the upstream side of my resistor. So another wire connected to pin 2 as well. Okay. So I go I put this jumper wire into pin 2, into the same row as pin 2, feed it through, and I'm going to come into this push button switch, and I'm going to mount this in the same row as the upstream side of that switch. The downstream side of that switch then goes over to ground. Okay? And again, you're just going to have to refer back and forth to your circuit diagram over and over again to get this right. Okay, I'll comment that you are probably noticing some edits in the video, and this is because I'm having to stop and start so much, and I apologize for that, but unfortunately it's just a reality of how I'm filming and how I'm having to do things here. So at any rate, we have now successfully taken care of pins 1, 2, and 8. So now we're going to work our way around to pin 3. Pin 3 from our schematic says that we should go to a 220 ohm resistor, and the value is really not that critical. It could be a 330 or a 220 through an LED down to ground. The order of that really doesn't matter either, by the way. You can actually put the resistor after the LED, but that's fine. So I'm going to reach for my 220 ohm resistors that I have separated out. And again, I will confirm that it is a 220 ohm resistor before I put it into my breadboard, because I don't want to risk having put the wrong value in. So I'll place my resistor flat on the surface, and I will measure its value. And I measure it to be 218 ohms. That's close enough. And so what I'm going to do is actually just put one leg of the resistor in the same row as pin 3 of my timer chip. Okay, and then I'm going to bend that other leg down and insert it into another row on my breadboard. I'm going to get an LED out, doesn't matter what color it is. By now you should have learned that there are actually 2 ways to tell which is the positive side and which is the negative side of the LED. The way I'm always looking at it, for this particular style of LED at least, is that if you look at that plastic case, at the bottom of it, there's a ridge that goes around. One side of that has a flattened side. So if I look at it from underneath, I can actually see it a little better. But this ridge that goes around the bottom of the case, there's a flat side to it. That's the negative side of my LED. Okay, and so I'm going to go ahead and insert that with one leg into the same row as the resistor, the other leg into another row on my breadboard, and then I'll use a jumper wire again to connect that downstream side of the LED over to my ground connection. Okay, like so. Alright, so we've dealt with pins 1, 2, 3, and 8. Pin 4 is pretty easy because we just need to apply 5 volts to it. So I'm going to again take a jumper wire, look at pin 4, and then I'm coming over to my 5 volt rail. And you can see already we're getting some spaghetti wire. And we'll talk about how we trace our circuit in just a couple of minutes there. Alright, pin 5 has that 10 nanofarad capacitor on it that goes to ground. As I said before, any of these little capacitors in your electronics kit that's in this little plastic storage box, pretty much any of those will work. So just pick one, doesn't matter which one it is. I'm going to put one leg into the row with pin 5, the other leg in a row below it. Okay, and again, I will use another jumper wire to go from the downstream side of that capacitor over to my ground connection. Okay. Okay, pins 6 and 7 are supposed to connect between this 100K resistor and our capacitor, which means we need to put our 100K resistor in place. Okay, so I'm reaching for my pouch that has my 100K resistors. Actually, that's 10K. Hence why we label our bags to make sure that we've got everything correct. So there's my 100K bag. Pull out a resistor, and this is the one that you want to make sure you measure accurately. because this one will affect your results and your calculations and everything. So do not accept that it's 100K exactly. You're going to measure this and record this value. In my case, mine is measuring 98.8 kiloohms. All right, so 98,800 ohms is what mine is measuring. Yours may measure a little different than that, but record that value because it is that value that feeds into the equations. Okay, now to attach it to our capacitor, we could do a couple of different things. I'm just going to take one leg and put it into the upstream side of my capacitor. And then the other leg I will put in a row up here. And then I just need to charge that from my power supply. So I'm just going to run a jumper wire from the top of that resistor over to my 5-volt rail. Okay. Now I could have gone ahead and taken this jumper wire and run it up to pin 8 just like I've drawn it. But either way, it works fine. So pins 6 and 7 now are going to both connect to the upstream side of that capacitor. They're going to connect to the junction between the resistor and the capacitor. I'm going to try to use two different colored jumper wires here so that we can distinguish those. And so I'm going to use a green wire and an orange wire. And so it doesn't matter which one goes to which. So pin 6, I'm going to plug in there. And then I come down here and I'm looking for that row that is between the resistor and capacitor, and I plug the other end in right there. Okay, and then this one I'm going to plug in there, and then this end should go up to pin 7. You have to take a lot of care here. Alright, I have now successfully assembled my circuit, but I'm not going to power it on yet. That's not what I do. Okay. Some circuits are not forgiving if you've hooked up things incorrectly, and you can short circuit things, you can fry components and so forth. So I'm always going to check my circuit, and especially when you're using an integrated circuit chip like this one, there's a couple of different ways of doing things. I will show you my method of doing things. Again, my 2 index fingers, as I showed you last week, help out a lot. Okay, so what you'll notice here is pin 1 should be connected to 5 volts. I'm sorry, pin 1 should be connected to ground, but nothing else. Okay? So I want to confirm that pin 1 has a single connection to it. Okay, so there should be nothing else connected to pin 1. So all I see is a single jumper wire in that row, and that jumper wire I verify by tracing it with my fingers goes over to ground. Pin 2 actually has a couple connections to it. Pin 2 has a connection that goes up to this 10K resistor. Alright, so pin 2 has a connection that goes up to this resistor, and because I've drawn my diagram similar to how I've put the components on my breadboard, that makes it easier to trace. So this connection from pin 2 goes up to that resistor, and the upstream side of that resistor is going to 5 volts. Always verify that your connections are in the same row. It is easy because of parallax to be off by a row. So you always want to check for that. Okay. Pin 2 also needs to be connected to a push button switch that's connected to ground. So pin 2, in addition to the yellow wire, does have a green wire connection. I follow it with my fingers, and it comes down to this push button switch, and I verify that it is in the upstream side of that switch. And then the downstream side of that switch I verify has this blue wire in the same row, and it's going to ground. Pin 3 is supposed to go to a 220 ohm resistor to an LED to ground, but there should be no other connections. So there's a single connection to pin 3. So that's the first thing I want to verify, is that there's only one connection to pin 3. Okay, and I'm now looking for it to verify it, and there's no jumper wire there because I put my resistor there. Okay, so I've got my resistor coming down, and I have to kind of nudge my wires apart a little bit so I can see, but the resistor is connected to my LED here, and out of the LED comes a jump wire that goes to ground. So that gets us through pins 1 through 4. Pin 5 should go to a capacitor that then goes to ground. And so I verify that I've got my upstream side of the small capacitor in pin 5. The downstream side is connected to this jumper wire, goes over to ground. Pins 6 and 7 should be connected to my RC network over here, my RC charge and discharge circuit. And so here's my resistor and capacitor that's charging, and you'll notice that I've already forgotten something. This is why we do this. The upstream side of my resistor is connected to 5 volts as it should, but the downstream side of my capacitor is supposed to be grounded, and it's not. This is why we check our circuits before we energize. Okay, so I'm going to take my jumper wire and I'm going to go from the downstream side of my capacitor over to ground. So now my RC network is connected as it should be, so it's going to charge and discharge, and pins 6 and 7 should be connected in between there. So pin 6 is this green wire, and I'm going to verify that it's in the same exact row, and it is, and it goes to this same row that's between the resistor and the capacitor. Pin 7 should also go to that same location, and it does. And then pin 8 should go to the 5 volt connection. Alright, I've now checked and double checked as much as I can, so I'm going to go ahead and energize my circuit and test things out and see how it works. Now if you've done your calculations up front, you should be expecting this to stay on for a certain amount of time. I'm not going to tell you what that time is. Okay, but I've plugged my battery in, I've energized my circuit. If your LED comes on whenever you first power on the circuit, you've obviously got a wiring problem. It may not mean that you've hooked something up incorrectly. What it may mean is that you've got a bad connection. I did have that happen earlier this week, and as I was testing things. If that happens, make sure that all of your wiring and components are seated properly. If you jiggle the wires and the LED goes off, that means that you've got a poor connection somewhere. Okay, but assuming I've hooked everything up correctly, then whenever I push this button, my LED should come on. And it does, and it should stay on for a certain amount of time based on that RC time constant and the equation that goes with that. So it should be 1.1 times the resistance times capacitance, and you see it is shut off on its own. Okay. Now here's where you're going to time how long it stays on, and you'll use a stopwatch. You can use your phone, timer, whatever. And so the moment you push the button, you start it and you time how long it stays on, and then it goes off accordingly. Okay, so you're going to do that multiple times, measure that, and see how well it goes. Okay, now having done that, what you're then going to do is replace R1, that's this resistor. Okay, and so we're going to de-energize the circuit, and we will take out that resistor. Okay, this was a 100K resistor. All right. And so what we're going to do is take that out. We will refer back to the handout, and the handout says that what we are supposed to do next is to replace that with 2 1 mega ohm resistors. Okay, I'm sorry, pardon me, a 1 mega ohm resistor first. Okay, so I'm going to place a 1 mega ohm resistor in its place, and then I will make the same measurements again. It's going to stay on for a longer period of time. And then thirdly, we're going to take that resistor out again, and this time instead of 1 mega ohm resistor, we're going to put 2 of them in parallel. And the reason we're doing that is our electronics kit is a little limited into the values of resistors that we have, and so these 2 1 mega ohm resistors in parallel are going to give us another resistance value that lies between 100,000 ohms and 1 mega ohm. So that's why we're doing that. And so because those resistors are in parallel, you'll need to measure and calculate the equivalent resistance of those 2. All right? So whenever you place those 2 in parallel, and I'll demonstrate for you how that works, but it's easy enough. You're just going to take 2 of the 1 meg resistors. You will measure their resistances to make sure that they are 1 mega ohm resistances, give or take, within their tolerances. You will record those values. Okay. So my first one has a resistance of 992,000 ohms. My other one has a resistance of 997,000 ohms. And so what I'm going to do is place them in parallel with each other. Now this gets to be a little dicey. You want to make sure that you've got enough breadboard slots available. So this jumper wire here, I'm going to slide it over so that it's next to this one. So my upstream side of my resistor has to be here. And I'm going to actually move this one over so I can see things a little bit better. So my upstream side of my resistor has to be at the same place as my 5 volts is going to come from. And my downstream side must be in that same row as the capacitor is connected to. Second resistor, same story. It's in parallel. So that means that the upstream side and the downstream sides must be in the same rows on my breadboard. Just bend things appropriately and slide that in. Now as you do that, double check, make sure they're seated, make sure you didn't knock the capacitor loose. Again, power the things back on there, and you can test by pushing that, and now it should stay on a little bit longer than it did before, which it will, but that'll be based on the new value of this value of R1. R1 is not going to be a single resistor this time. It's the 2 resistors, but they have an equivalent resistance that will be a value for R1. Okay? Alright, so that gets us through part 1 of the experiment. That's what we call monostable mode. Now we're going to talk about the astable mode of our circuit. Okay, so before we make any changes to our circuit, we're going to de-energize, and so I'm going to go ahead and turn the power off and to make sure I don't do anything incorrect. And I'm going to refer to my 2 circuit diagrams side by side, and you'll notice that a lot of things are the same as they were before. There are a couple of differences though. Alright, so let's compare and contrast. I'm going to move my breadboard out of the way here so I can see what's going on. Okay, so as I lay these side by side, this is my monostable. I'm going to label it so I don't get confused. This is my astable. Okay, notice that over here on the right hand side, this is pin 3 here. This is that output pin. Notice that has not changed in the 2 circuit diagram, so I don't have to make any changes to that. Pin 1, which is my ground pin, that hasn't changed. My VCC pin, which is pin 8, that has not changed. Okay, so already I can see that I'm not going to have to change everything, but I do have to be careful. My control pin here has not changed. Okay. Now one thing that has changed is my RC network over here. Instead of a single resistor now, I'm going to have 2 resistors. Okay. So that is one thing that's different. And then this other branch here with pin 2 has changed around. Before we had this resistor up here and so forth. We no longer have that. Okay. So it looks like what's happening is that pins 6, 7, and 2 all have the potential to get mixed up a little bit. Everything else is the same. Okay, so what I'm going to do is I'm going to redraw again what I had before. So I'm going to sketch it. I know this takes time to do, but I promise you it is worth it. Okay, so again I'm going to have my 8 pins. I'll have my power supply over here. Again, I'm going to have my capacitor for my RC charging down here, and I'm going to keep that same capacitor, by the way, so it's going to be 100 microfarads. Okay, I'll try to make sure to keep this in the field of view, but if I don't, my apologies. But now this time, C1 is going to be connected to, I've already got my pages mixed up. Let me grab the proper circuit diagram. This is why we labeled them. C1 is going to be connected to 2 resistances upstream of it. And they will be in series. Okay? And they will go around and they will connect to my 5 volts over here. This will be R1. It's going to be a fixed value. We're not going to change this one around. There's my multimeter telling me it's about to turn off, so that's going to be my 1 kilo ohm resistor. I'm not going to change that. R2 is what I will vary this time. Okay, and so I now need to ground the downstream side of that capacitor. Pin 1 also needs to come to ground as it did before. Okay, pin 3 does not change. It's going to come down to this resistor that's 220 ohms. In this particular circuit diagram, that one is labeled R3, and then it needs to go to an LED and then to ground. Okay. Pin 5 has not changed. It has its capacitor there, that 100 nanofarad capacitor or 10 nanofarads, whichever it is, 10 nanofarads, so 10.0. And it needs to be grounded on the lower side. Okay, pin 8 needs to go to power, so I'm going to bring it over. Pin 4 needs to go to our 5-volt power supply. Okay, so pins 2, 6, and 7 are really where the main changes are happening now. Okay, so let's pay attention to what's going on here. So in my astable mode, my discharge pin needs to connect between these two resistors. Well, my discharge pin, if I refer back to my data sheet, my discharge pin is pin 7. So pin 7 here needs to connect here between these two resistors. Okay. Then I refer here, my trigger and threshold pins both connect to the upstream side of my capacitor. Well, trigger and threshold are pins 2 and 6. So pin 6 will come down, connect there. Pin 2, and I'm going to have to, draw across there and make sure I connect it properly. Alright, so I now have a working circuit diagram that really doesn't require me to change a whole lot. So again, pins 2, 6, and 7 are the pins where things change. Now, what I tend to do to make sure that I don't make as many mistakes is I'm going to totally remove everything connected to those pins on my breadboard. I'm going to grab the boots of the jumper wires and I'm going to remove those wires totally from the breadboard. I don't want to get confused and leave those connected. Okay, so pin 6 and 7 go away. I have no connections to them now. Pin 2, before it was connected to this resistor and to this push button switch. Okay, so I'm going to remove that jumper wire totally from my breadboard so I don't get confused. I'll remove this jumper wire that was connected to pin 2 up here. Even though I know I'm going to put another jumper wire in there later, I don't want to get confused. So I'm going to remove it by pulling on the boot of the jumper wire. I'm going to remove that push button switch. I don't want it in the way. I want nothing in the way that's going to confuse me. And then on the upstream side of pin 2, I'm going to this resistor. I'm going to pull that jumper wire out. I'm going to remove that resistor, get it totally out of the way. I'm going to remove that jumper wire. So I have no clutter in the way. Okay, my resistors that were here present prior, I'm going to remove those. And now I'm ready to first begin by assembling my resistor capacitor network here. So I'm going to remove that jumper wire that went to the upstream side of my resistor capacitor network. So I've got C1 in place. That's still that same capacitor. Now I want to get a 1K resistor, and then I want to get my value of R2, and for the first one I'm going to use is going to be 5K. Okay, so a 5K resistor. Alright, so I'm going to go ahead and get my 1K resistor first, and I'm going to be searching through my packs looking for that 1K resistor. And I've got my envelope that's labeled accordingly. I'm going to get my 1K resistor. I will measure its resistance. I need to record it because this does become part of my calculations. So I'm just showing you that I will measure it in order to know exactly what it is. Mine's 991 ohms, which works fine. And then I will also go ahead and put it into the breadboard so I don't get confused about which one this is. This is R1. So I'm going to place it into the breadboard like so. Since it is R1, it's not the resistor that connects directly to the capacitor. So I don't want to put it too close there. R2 is going to be my 5K resistor. Again, I'm going to get my Ziploc bag with my 5K resistor. I will measure its resistance exactly, again, because that becomes part of the calculation. Straighten it out. The resistor legs are pretty robust. They can handle being bent back and forth a little bit, just don't get too rough on them. And that measures 5.05 kilo ohms. Okay, now this is going to be my R2 value, so that means that the upstream side of this resistor must connect to the downstream side of R1. The downstream side of this resistor must connect to the upstream side of my capacitor. Now, if my resistor can't reach there for some reason, it's okay just to shift everything down. In fact, if you want to put R2 in first, that would have been fine. Okay, so I'm going to put R2 in there, and I think it's going to reach just fine. Okay. Now I'm ready to reconnect the upstream side of R1 to my 5 volts. So jumper wire, upstream side of R1, and then I'm going to go over to my 5 volts. Okay. Alright, now, having done that, we now need to go ahead and make those connections between pins 2, 6, and 7. Alright, pin 2 connects to the junction of the resistor and the capacitor. So I'll get my jumper wire out, and I will pay attention to the fact, I'm going to disconnect this barrel jack so I can tip this so that you can see a little better what's going on. There should be nothing in with the pin 2 connection at the moment. So I want to confirm that there is nothing in that row besides pin 2. I'm going to put a jumper wire in there, and I'm going to ensure it's in the row with pin 2. And then I'm going to feed this over to connect to the row between R2 and my capacitor. Okay, that takes care of pin 2. Pin 6 connects to that same location. Alright, so again, I'll take a jumper wire, make sure that there's nothing in the row with pin 6, because there should be nothing else there. And then I'm going to place that jumper wire into that row with pin 6, bring it down to that same row again, and to leave some room for myself for later, I'm going to go ahead and put it here in the middle. Well, not in the middle, but next to that first jumper wire. Pin 7 is supposed to connect between the 2 resistors. Okay, so I'm going to go ahead and verify again that there's nothing in the row with pin 7. I place my jumper wire in the row with pin 7, and now I come to this junction between the 2 resistors, and I'm going to put it my jumper wire in that row where those 2 resistors have a junction. Okay. Alright, I've got things hooked up. Again, I don't energize the circuit until I have checked it thoroughly. Okay. And I'm going to check every connection, even the ones that I didn't mess with. Alright, pin 1 should be connected to ground and to nothing else. Pin 1 has a jumper wire on it. There's nothing but the one jumper wire. It goes to ground and there's no other connection. Pin 2 should connect to the junction between R2 and C1 and nothing else. There's no other connection to pin 2 except this one, and it does go to the junction between the resistor and the capacitor. Pin 3 should go to a resistor, to an LED, to ground. Pin 3, there's my resistor, and there's nothing else in that row except that resistor. It goes to this LED. I confirm that the downstream side of that resistor and the upstream side of the LED are connected. Downstream side is there, jumper wire from LED to ground. Pin 4 should go to 5 volts and nothing else. There's only one connection to pin 4, that's good. And then pin 4 goes over to 5 volts. Pin 5 should go to a capacitor, to ground, no other connection there. So I verify that there's only one connection in the row with pin 5. There's that capacitor. Here's my jumper wire that is in the same row as that capacitor, and it goes to ground. Pin 6 should go to the junction between R2 and C1 and nothing else. And I verify that there's only one connection with pin 6, and it does go indeed to the connection between R2 and C1. Okay, and then pin 7 should be connected to the junction between the two resistors and nothing else. I look at pin 7, I see there's only one connection, it's this green wire. I trace it physically, and I see that it is in the same row there. And then pin 8 should go to 5 volts and nothing else. Pin 8 goes to our 5 volt rail, nothing else. My upstream side of R1 should be connected to 5 volts. I'm going to verify that that's the case. And my downstream side of my capacitor should be connected to ground, which was a mistake I discovered a while ago in checking my circuit, and it's still there. Alright, having done that, I am ready to energize my circuit, and if all goes according to plan, I should have a blinking LED. And I do. Now if yours doesn't blink, again, check your wiring, check your connections, make sure that everything is as it should be. But the frequency of that should be predicted by the equation that's in your data sheet, but we'll cover that equation in class. Now at this point, the handout calls for you to time these flashes for 5 minutes. Okay? And the purpose for that is to get some good statistics. All right? Now let's talk about how that works. All right? Don't do this. Don't turn it on and then start counting. The reason for that is because of the amount of time it takes to charge the capacitor up the first time. There is a time lag. Okay? So have the circuit energized and let it have already established a blinking pattern before you start timing it. Don't forget, this is a repetitive wave function, so just like in Physics 200 when you did waves, you count peak to peak or trough to trough. Okay? But make sure you're careful about this. So for instance, if I'm going to start timing my first, and I tend to time when the light comes on. But when it comes on the first time, that's not 1, that's 0. Okay? So 0 is the first time it comes on. That's when you're starting. When it has completed a full cycle and it's gone dark and then it comes on again, that's 1 completed cycle. So when you start, that's 0. So don't get in the habit of saying 1. Whenever you start, say 0, because that's your starting point. So if I'm timing this, what I'm going to do is I'm going to kind of get into rhythm where I'm about ready with my stopwatch, and I'm tapping my foot to keep me honest. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you'll count that for 5 minutes. Based on that, you can get the frequency and compare that to the predicted value based on the equation. Okay? And it's kind of rewarding to see this happening. And so it's kind of neat to be able to see that LED blinking and to realize that you've created a circuit now that does something that's kind of fun. Okay? Now we adjust that frequency based on our choice of R1 and R2. For purposes of our lab, we're going to keep R1 the same, and we're just going to adjust R2. And again, because we have a limited number of values of resistors in our kits, what we're going to do is to have R2 replaced initially with a 100K resistor, so 100 kilo ohms. And then, in order to get another value of resistance in between the 5K and the 100K, we're going to put my apologies. We're going to replace it with a 10K first, then we're going to take 200K resistors to put in parallel. Okay? So the two 100K resistors in parallel should have a resistance of roughly 50,000 ohms. So that's what we're achieving here. So you'll have an R2 value of 5,000 ohms initially. That will give you a certain frequency. You're going to replace that in step 7 with a 10K resistor for R2. Okay, that will give you a different value of frequency. And then you're going to replace R2 with two 100,000 ohm resistors, which gives you an equivalent resistance of roughly 50,000 ohms, but you'll need to know that number exactly. So again, just like with the monostable, you'll need to put the two resistors in parallel with each other. And if you need to go back to the earlier part in the video where I demonstrated that, rewind and look for it. But basically, you're just going to take out R2 and you'll put the 200K resistors in parallel next to each other to achieve an equivalent resistance of roughly 50,000 ohms. Okay? Alright, having done all of that, you have successfully navigated through your first spaghetti wire experiment. The cleanup afterwards is just as important, and so what you want to do is remove all your components, de-energize your circuit first, obviously disconnect power, and I tend to remove my breadboard power supply first, place it back in its holder there. Remove the battery clip and place the battery in its clip holder back in there. And I've got several components that are going to be going back into my little plastic box, my 100 microfarad capacitor, my LED, and then the smaller capacitor up here. Okay. And then it's a matter of removing jumper wires. Again, remove those at the boot level. Do not grab the wire apart. You're more likely to pull the wire loose from the tip at the end, so just remove them at the boot level. I know it can be a little tight to fit in there sometimes to grab at the boot level, especially when you've got several wires side by side, but I promise you this is the way to get the longest life out of your jumper wires. If you're in the habit of pulling the wires, you will have a problem there. Okay. Remove the resistors, and you'll have to sort those. I'm going to have to measure all these resistances before I put them back into my baggies so that I keep them sorted. And then, as I told you earlier, your 555 timer chip, if you don't have a chip puller, which most of you aren't going to have that, you can use your thumb and forefinger here, index finger, but do not wedge away from you or towards you. Do your very best to pick straight up on that chip, so that you don't bend the legs. If you do bend them, you can use needle nose pliers or tweezers or something like that to straighten them back out. Okay. Well, with that, that's all for lab this week, and hopefully you're going to have success. You'll be making some measurements, and you'll have something fun to illustrate for friends and family that you actually do build something that's useful in electronics every so often. So we'll be seeing you in class, and hope your lab exercise goes well.